We'll be doing a quick tech demonstration on it. This is a little gear bottle opener part that we like to do. It takes about 10 minutes. We'll give you a general idea of the capabilities of the machine. But as well, I'm just curious for everyone who's on, what you're looking to learn doing the demonstration today.
So unfortunately, Steve couldn't make it.
Okay.
But we still wanted to see this, and we'll have to relay a lot of the information to him.
Okay.
But I think we just kind of want to know what the capabilities are and what it's like to set it up and get it running.
Okay. Perfect. So what we'll do then is we'll get started here. We have the control up on the right-hand side here, and then the machine is running over here. So just let me make sure that you guys can hear me okay. If you can't, let me know. As you can see, we're having some technical difficulties today, so if the audio cuts out or anything, just let me know. So what we're gonna start with is just an overview of, we can start with the machine construction just to let you know a little bit more about that. So the Neo is our smallest machine in the lineup. This fits through a standard doorway. It's a small footprint machine, but it has a pretty large work envelope considering its size. So it has about a 20 by 16 inch work envelope with about a 7-inch total height on the inside. So you could fit some pretty sizable parts considering its sort of minute footprint. And its construction is all polymer concrete. So this whole bridge portal assembly here is polymer concrete with linear ways on all axes with direct drive ball screw motors. We've got a 2 kilowatt, 40,000 RPM spindle and a 24 station tool changer. So your 24 stations are back here, integrated measuring posts, and then we have a touch probe here as well that we'll get into a little bit more in a moment. And then just to talk about sort of the capabilities, the accuracy for this machine is somewhere in the 25 micron range over its work envelope, so about 1/1000 of an inch. And then its repeatability is somewhere in the 3/10 range, so about 8 microns. So very accurate machine, also very fast. So max rapid's about 1100 inch per minute, half a G acceleration. So you'll see once we start using it, it's very quick to change tools and position from location to location really smoothly and very efficiently. So next, I'll touch on the control, which is really a shining point of the Neo. This is the DATRON Next control, and it's extremely easy to use, especially for a non-machinist. So if you're an engineer, a designer, a student, something like that, Next gives you the sort of capability that you normally wouldn't have stepping up to say you stepped up to a Haas control, something like that. There's a much more steep learning curve with that because it's a very industrialized, sort of typical interface, where this is designed to be a bit more like using a smartphone or a tablet or something along those lines. So the Next control will walk you through every step of the way for when you want to run a part. So I'll start here. You'll see it here on the right side of the screen. I don't know if you can see my mouse or not. So we'll use Cam Assistant. Cam Assistant is a really good way if you're a new user to sort of hold your hand step by step in loading and running a program. So you'll start offline with a CAM software, something like Fusion 360 by Autodesk, or any of the industry standards, Mastercam, Gibbs Cam, SolidWorks Cam, anything like that will work just fine. And you'll post out a file generated from the CAM software, and then we'll run it in here. So we start by going to the CAM wizard, and then we'll go to load in a milling program. So I'm going to pick from my library. Oh, sorry, actually I'm going to go to Quick Link. I'm going to load in bottle opener 2019.simple. Simple is the file format that DATRON works with natively. And to give you an idea of what that's like, the industry standard is G-code, which we work with, of course, as do all CNC machines. But we have a format that we work with CAM developers to create a post processor to output directly in our simple format. And what that lends us is the ability to output a lot of really useful information. So this is the simple file in the background. And this has all the information about our cutting tools, about the workpiece dimensions, where the 0 is located on that, the sequence of events, and then sort of subroutine callouts. So if I wanted to go and change, say I wanted to change a variable for cutting feed rate or something for RPM, I can go and change things very quickly here instead of having to dive through a big, large G-code file, which can be kind of cumbersome. And then the actual cutting file is really straightforward. So for linear moves, line X, Y, Z. For circular moves, it's arc, clockwise, counterclockwise, RPM call out, tool changes. It's really pretty intuitive. So it looks a little bit different and almost intimidating at first, but it's actually quite easy to get used to and accustomed to. Everyone following along okay with me?
Yes.
All right, perfect. Any questions along the way, just feel free to shout them out and I'll answer them.
Yep.
All right, so the next step in the Cam Wizard is running through the tool check. And what it's doing is in that program, at the very top, it calls out all the cutting tools that we need in order to run that program. And by having all that information, it's able to tell us whether or not we have all of the tools already loaded in our machine or not. So in this case we do. Obviously we're prepared for our demo here, but if we didn't, it would tell us whether we've used it before and it's in our warehouse, or if it's never been used before and it's unavailable completely. So it will highlight that and say you have used one in the past and you can select it, find it in your storage, and load it into the magazine. But just as well, if you have none of it, then what it will do is it will say maybe you have a tool that's similar. So if you have a tool of similar cutting diameter or something along those lines, it will say you have a tool with similar dimensions, and it will make a recommendation on it, and it will highlight the differences between the tools. If there's a variation that may not work, it will bring it to your attention. So in this case, we're all set. If you had to load tools into the machine, it's quite easy. We go to our main menu here, and under Tool Management, it's really straightforward to just go and search for a tool and add it to your magazine. The whole DATRON tool catalog is already added to the machine, and then you have the ability to have a user catalog. So if there's a certain brand of tool that you like to work with, you can go and enter that information into the user tool catalog and add special tools or drills or ball mills, any type of tool really, add it here directly into the machine. But in this case, if I wanted to go and add, let's say a 68406, it will say, all right, you don't have any in the tool magazine, you don't have any in the warehouse, there's one in the DATRON tool catalog. And I can go and grab all that information, and then I can say create that in the warehouse or create it in the tool magazine. So when I do that, it tells me, it pre-populates all the fields that are important for that tool. If I wanted to throw a particular comment in about that tool, I could, but otherwise I don't need to. And then I'll say save, and it will actually move the machine to its tool opener position, and you can see here it highlights number 8 as an available spot. So right here, number 8's available, so it's telling me I can go and load that tool in that position right now. So it walks you through every step of the way to make sure that you're not just sort of guessing, relying on your knowledge. It gives you nice visual cues to make sure that you're doing it the right way. So in this case, I'm not going to load a tool, so it's going to cancel this transaction. It's going to move it to the warehouse, which is just fine. All right, so to get back to Cam Assistant. So we have all our tools. Then we have the option of measuring all our tools. They've all been measured recently, so I don't need to. So in this case, I'm going to go to my next step. Now this is where we set up the workpiece origin with the touch probe. So this is probably one of the most user-intuitive features of Next that we're kind of well known for, is the extreme ease of use in probing. So instead of having to hand jog the machine over, all I need to do is drag my finger across the screen. So I don't know if you can see, I'm going to move the camera over just a scotch. So you can see the machine and the screen and the way I'm interfacing with it. So I'm just dragging my finger across the screen, and that's how I jog to where I want the machine to go, and I see what the camera sees, of course. So now I'm looking at that piece of stock on the right. So I just zoom in on it, and based on the file that came out of Fusion 360, the simple file, it's telling us that the workpiece is about this size, and that its origin is located on the top center. So you can see that here, programmed origin of the workpiece, top center, so I know exactly where I need to probe. So now instead of having to type in numeric offsets or anything like that in order to probe this, all I need to do is just draw the feature that I want to probe. It doesn't have to be real pretty either. I just draw a circle, and it plots out a circle. So I can drag this to fit that circle. And then I have 4 points here that will probe along the outside, and I just drag these wherever I want. So if this is in the way here, I drag it in and over so it's out of the way of other stock or fixture or anything like that. So it's very user intuitive, very friendly. Then the probe drops down and touches off on those 4 points. Sorry, I keep hitting my mic here. It sounds loud. So it's really quite simple in that way. And just to show you, it doesn't just do circles either. If I wanted to do a corner, for instance, or a rectangle, inside, outside, if I wanted to do perhaps a circle over here and then a circle over here, where this comes in common practice is when we cut a sheet out on the vacuum table and we want to probe 2 bores that we milled. We probe one for origin, and then we probe another to find the rotation of that part. So we can do that. We can also do a circle and an edge, or an edge and an edge, and find the symmetry of a part. So you can see it's really pretty straightforward. And it allows a lot of capability to a user who would otherwise be pretty helpless on, say, a Haas or a Mazak or anything where you're learning sort of standard Renishaw probing routines. They can be quite tricky by comparison and very expensive when you have an accident. Something that's kind of interesting about our probing system that you don't really see on others is this magnetic tip breaks away. So if I have an accident and I hit the probe for some reason, even though it seems pretty intuitive, accidents still happen, it has a little magnetic breakaway clutch. So it just disengages completely, and then all I have to do is pick it up and reinstall it and possibly recalibrate. But you can see here, 5 seconds later, I pop it back on and the probe is good to go again. Moving on from there, we'll go back to the Cam Wizard. So we've already probed that, so we're all set here. If we had to turn on our vacuum source at this point, we could. That turns on a 24-volt relay to turn on or off your vacuum pump. Everything else is set, so we go to our next step, and it gives us a 3D simulation of the part. This is all generated from the code. None of this is, there's no solid model or anything passed through from the CAM software. It's generating this purely on the dimensions of the workpiece and the tool path. So we can get a really good idea of how our tool looks in the end, how our workpiece looks in the end after milling. Just another level safety factor to make sure that your parts are going to come out the correct way. Sort of goes on top with the CAM generated simulation. All right, so I'm going to leave up this screen, and I think we're going to cut the part right here, unless you guys have any questions before we continue.
No, I think we're good.
All right, so we'll press play. So I'll just give you some information on this part as we run through. You can see here on the screen, that's a 6mm single flute end mill, spinning at 35,000 RPM and running at 6 meters a minute. Then you can see at the nose of the spindle there, we have two angled nozzles there, and that's our coolant system. That's spraying evaporated ethanol coolant mixed with air. And so as we spray that, it's hitting the cutting tool and it evaporates with the heat generated from the cut. So you end up with clean, dry chips and really no cleanup. When you're done, all the chips just sort of accumulate down in the bottom of the machine. So there's really very little work to be done after with degreasing a part. They come off quite nice. We're taking a finishing pass here on the outside. This is where the high dynamic features of the machine become really apparent. Its ability to quickly accelerate and decelerate is in, this is called an adaptive clearing move. There's many variations of this in different cam software, like Mastercam has dynamic motion, for instance, where it's sort of spiraling all the way down into the cut and then taking a sort of a full depth of cut in a pocketing procedure. So it more efficiently uses the long cutting flute versus only using just the tip of it. So it's really a more efficient way to remove material, as well as better for tool life. Other equipment can utilize this strategy as well. Our system does a little bit better at making the most of it because of its dynamic capabilities. Now we're using a 2mm single flute end mill, spinning it at 39,000 RPM and going about 2.5 meters a minute, which is about 100 inch per minute. And that's performing sort of a slot milling move where we're ramping our way down into this narrow feature. Something that our machine is particularly good at is we develop our own single flute end mill tooling, which is excellent for plastics and non-ferrous materials like aluminum or copper, brass, where normally a sort of gummy material would get caught up in multiple flutes. With this, you use one flute and have a much larger chip cavity, so better ability to evacuate chips. That was just a quick chamfer pass. Do a quick edge break on everything. This is a corner rounding tool, 1mm. So right now you can see that the part is set up to only pick up and put down the tool, but you can actually also have it do a length measurement before or after or both. So if you're pressed for time and tolerances aren't super critical, then you can have it just pick up and put down the tools. But usually the tool change is very quick on the machine, so we like to do a length measurement on top of it. We're back with that 6mm single flute right now, 35,000 RPM, 6.5 meters a minute. Some other useful information on the screen is it tells you what operation it's running on. So here we can see 2D contour 34_16, what line we're running on, the tool data, current axis position, what coolant system we're running. As well, we also have current cycle time and then estimated time until completion. You'll see this green bar actually drags across the screen on the top to give you an indicator, a visual cue from a distance of how close your job is to being done. As well, on the handheld remote, I can go and turn down the feed rate. So you see, as I turn up and down that on the remote, it represents that visually on the screen. Now we're cutting a thread here, a 632 thread, or maybe an 832 thread, going off of memory. So really lightning fast. That was about 35,000 RPM. Then just a chamfer edge break on everything. We're doing an engraving here with a 0.5 millimeter double flute ball mill. 38,000 RPM, 1.5 meters a minute. So that's 60 inch per minute. And that's it, 8 minutes from start to finish. You can see there, that's our finished part. I don't know how good that looks from here. Let's see if this focuses. Probably not, huh? Oh well. I'm gonna use my hand model over here, Eric. Thank you, Eric. Oh, no, a little further down. We'll send you pictures.
Perfect.
Okay. Hopefully that answered most of your questions, but let's take a few minutes just to, there must be some other questions that popped up during the demonstration that we have time to answer now.
Yeah, so unfortunately for me, since I don't know much about this stuff at all, like, how, this is probably a simple question, but I'm gonna ask it anyway.
Sure.
How, does the software tell you how to cut the part that you want?
Good question. So what we have, I'll have to see if I can log on and share this with you guys, or I might just send you a link afterward with some documentation. But we have a feed and speed guide that we recommend to any of our users running aluminum specifically, or plastics even, where it walks through cutting recommendations for our single flute end mills, for aluminum specifically, but you can utilize it for plastics as well. And it gives you an idea, depending on what style of cut you're doing. So it gives you a recommendation for particular spindle for the machine you're using. So it would walk you through the 2 kilowatt for the Neo, and a particular tool size, and then a particular feature type. So if we were doing a pocket milling feature here, it would have one recommendation, versus if we were doing a slot milling like we did inside the spokes here, it would have a different recommendation. And that's what we like to share with our customers to get them up to speed with the ins and outs of programming for using a DATRON, because it is a little unique compared to others. There's a lot of other tooling vendors out there that supply their own recommendations for feeds and speeds, but they're usually more favorable for a low RPM traditional machine. So we supply that guide, but as well, we have a pretty big applications group here, about 5 or 6 of us. And we're pretty used to us ourselves getting files from a customer and saying, hey, I'm working with a new material or new tooling. Can you give me a recommendation on that? And walking them through, giving some basic recommendations for that. So that's generally how it works.
And then, so I don't know how much Steve told you or how much you got from what he was actually interested in, but I think this would be used a lot for making small little molds, injection molds or compression molds.
Yep.
We usually make them out of aluminum, so the material shouldn't be an issue.
Yep.
But our parts are small.
Yep.
So I just don't know what the capabilities that are there as far as what your smallest end mill is or smaller end mills. And
Yep. Yeah, so I talked with him about a week ago or so, and we talked about what the smallest feature is on the parts, the molds that he's making. And by the sounds of it, it was like the smallest feature was about 0.5 millimeter wide. And the good news is that we're capable of going down to 0.1 millimeter for the smallest tool that we can touch off on the measuring post. We've, truth be told, actually touched off a little bit smaller than that. Just we can guarantee that you can touch off a 0.1 millimeter size. So that's about 0.004 of an inch. And that was plenty small enough, he said, for the application that he has in mind. And then the accuracy of the machine, I spoke to that with him, and the 25 micron positional accuracy, and then the 8 micron repeatable accuracy. And he said that those are both fine for the tolerances that need to be achieved with that.
Yeah. Yep.
Yeah.
I'm getting a chair. There we go. That's much more comfortable. Kind of tall. We're just configuring this for my height now. So yeah, based on the size of the features, the Neo is capable for it, for certain. We have other equipment that is capable of doing maybe even smaller features than that, but I think they would be overkill for the needs of those particular parts.
Yeah. Yep. Sounds like it.
Yep. Any?
Well, I don't.
Oh.
Yeah, I don't know if I have any other specific questions right now. Did you have anything else?
Well, it's used for plastic and metals, is that right? Pretty much.
Yeah. So, what kind of plastics or other materials have you done in this?
Oh. The list could go on for a while, but I'll say what's common to see for plastics is PTFE, UHMW, Delrin, ABS, even like glass reinforced plastics. To a certain degree, they're more abrasive for sure, so you have to change what tooling you use with that to be able to handle the tool wear that comes along with abrasive materials, but carbon fiber as well, PC board material. Really, there's no material that's an absolute no-no. Even things like steel, we can work with. We're just not going to work the same way we work with, this part. We wouldn't ideally be doing this out of steel. Smaller parts. So if for instance the molds that you were making were steel and they were still the same small features, it would be a good fit for the machine because even with steel you need high RPM the smaller a tool gets. Where it would make sense to have a machine like the Neo doing that sort of work. So yeah, is there anything common besides the aluminum that you'd be working with that you think you might be utilizing the machine for?
Not sure yet.
So I have some little 1/2-inch hydroxyapatite disc. They're a little bit of porous ceramic material.
Okay.
And we're currently working a CNC machine for it, but they crack at the very edge. It's going too fast or something, but I was wondering if that would be something we could use on this. And I'm sure just kind of play around with it.
Yeah, so it's a porous material you said? So it's before it gets sintered and hardened?
Yeah, a little bit ceramic style.
Okay. We've worked with ceramics quite a bit, actually, because we have a line of machines that we sold that were dedicated to dental implants. So it would do a lot of titanium and cobalt chrome, but also zirconia, for instance. And really, the two deciding factors with that for what you use for tooling and what you need for maybe dust collection or something along those lines is the material pre-hardened or after hardening? So before sintering or after sintering? And with either one, it's something we could do. It just, the capabilities change a little bit because with a hard ceramic, one that's post-sintering, you really need flood coolant to be able to wash away the dust as you create it. It's very, very hard, and it can be very taxing on tools, where before sintering, it's very chalky. It's almost like milling like chalk or graphite or something like that, where it's just dusty. And it can be abrasive on tools too, but you can cut it with a pretty traditional end mill versus when you work with a hardened ceramic, you need diamond coatings or actual diamond bonded tools, almost like a grinding bit, sort of grinding wheel. So it changes how you approach it, but there's a lot of options, different ways to approach it, and we've spent a lot of time working with those materials in the past. Actually, having a high RPM spindle can be advantageous to working with those materials because grinding requires high surface speed. So not just high RPM, but how fast, how much distance the tool is covering when it's spinning. The smaller a tool gets, the faster you need it to spin to have the same amount of surface coverage. So we have some advantages in that realm.
Okay. Good.
Hopefully that answered your question and didn't create like 5 more.
No.
It's complicated.
Yeah.
So, any other questions?
Anything else?
I don't think so.
Yeah. I
Okay.
think we're good on our end. Steve couldn't be here today, and then our boss isn't on here either, so
Okay.
we'll talk it over with them.
Cool. Well, what I'll do then is I'll make up a few of these and send them to your attention. I'll make one for everyone. We're supposed to have 4 people total here today.
Yes.
Yeah. Well, we got 2. That's okay. So I'll make a few more of these and send them out in the mail, or Justin will send them along, something like that. And then I'll also send along that feed and speed guide so that you guys can see what you'd be working with starting off.
Okay.
Okay, good.
Very good. All right. Thanks, guys.
All right, thank you.
All right. Take care.
Bye.
Bye.